Every second, jet engines spinning at 12,000 revolutions per minute thrust hundreds of passengers across continents. But here's what defies physics. Inside those engines, turbine blades made of nickel alloy operate at 3,000 degrees Fahrenheit, temperatures exceeding their own melting point by 200 degrees. Picture holding ice cubes in boiling water without them melting. That's the metallurgical miracle happening 35,000 feet above your head. How does metal survive temperatures that should liquefy it? How do engineers grow crystals larger than your hand from molten metal? Stick around till the end, you'll discover the jaw-dropping secret of single crystal manufacturing that eliminated metal's greatest weakness, and why a single turbine blade costs more than your car yet lasts 20 years in literal hell. The story begins in specialized foundries where cleanroom standards rival semiconductor fabs. These facilities maintain air purity of less than 100 particles per cubic foot, 10,000 times cleaner than normal atmosphere. Even microscopic dust particles cause catastrophic flaws in turbine blades spinning at speeds where centrifugal forces generate stresses exceeding 70,000 pounds per square inch. That's pressure crushing steel like aluminum foil. Workers suit up in full-body cleanroom gear before entering casting halls. Inside, massive vacuum furnaces standing 2 stories tall and weighing 80 tons create environments replicating outer space. Vacuum pumps evacuate air until pressure drops to 1/1,000,000th of atmospheric pressure. At these conditions, materials behave differently. Impurities vaporize instantly. Gases trapped in metal escape, leaving behind purity impossible at normal pressure. Processing single batches costs $50,000 in electricity alone. Next comes mold preparation, where ceramic shells, think pottery on steroids, get built layer by microscopic layer. Technicians dip wax patterns shaped like turbine blades into ceramic slurry 10 times, waiting hours between coats. Each layer adds thickness thinner than human hair. After 20 days of coating and drying, workers melt wax away in autoclaves, leaving hollow ceramic molds with internal channels more complex than human circulatory systems. These molds contain passages narrower than spaghetti strands, designed to cool blades from inside during operation. Some channels measure just 0.008 of an inch across, thinner than credit cards. Manufacturing these passages requires such precision that lasers verify every dimension. One blocked cooling hole means blade failure at 300 degrees lower temperature. That's difference between safe flight and catastrophic engine disintegration at cruise altitude, scattering turbine fragments through fuselage like shrapnel.
Giant crucibles containing nickel-based superalloy. Mixtures of nickel, chromium, cobalt, aluminum, titanium, plus 6 other elements in exact proportions. Heat to 2,700 degrees Fahrenheit. Picture liquid metal glowing white like miniature stars captured in ceramic containers. This superalloy, developed through decades of research, contains more expensive elements per pound than fine jewelry. A single turbine blade uses materials costing $800 before any manufacturing begins. Robotic arms lower ceramic molds into this molten inferno with precision measured in thousandths of inches. Timing matters critically here. Pour too fast, turbulence creates defects. Too slow, metal solidifies prematurely. Furnaces tilt at exactly 2 degrees per second, filling mold cavities in 17 seconds. During this pour, metal temperature drops 300 degrees, requiring computer-controlled heating to maintain consistency. One temperature fluctuation of 5 degrees ruins the casting, wasting months of preparation.
Now comes the magic. directional solidification. The filled mold sits atop a water-cooled chill plate at 70 degrees Fahrenheit while surrounded by heating elements maintaining 2,400 degrees above. This creates the steepest temperature gradient in metallurgy, over 2,000 degrees difference across 6 inches. That's transitioning from Arctic to volcanic conditions in the space between your thumb and pinky. Slowly, incredibly slowly, a computer-controlled mechanism lowers the mold through the furnace at speeds of 6 inches per hour. Picture watching paint dry, then slowing that down tenfold. As the mold descends, metal solidifies from bottom upward in a razor-thin freezing front. This directional cooling forces crystal growth in one direction only, upward, eliminating horizontal grain boundaries where cracks normally form. The process takes 14 hours for a 4-inch blade. Rush it by even 10% and polycrystalline grains form, destroying blade strength. But here's where physics becomes art. At the mold bottom sits a grain selector, a corkscrew-shaped passage so narrow only one crystal nucleus fits through. As metal solidifies upward, countless tiny crystals form at the chill plate. They compete, growing upward like metallic trees racing toward sunlight. Most hit the spiral walls and stop. Only the perfectly aligned crystal, the one matching the spiral's orientation, passes through this metallurgical gauntlet. This step is critical because it ensures the entire blade, every atom from root to tip, belongs to one continuous crystal lattice. No grain boundaries exist anywhere. Normal metals contain millions of grain boundaries per cubic inch. Single crystal blades contain 0. Without boundaries, there are no weak spots where atoms slip past each other under stress. The crystal structure extends uninterrupted through the entire blade like a 3-dimensional molecular Kevlar vest, with atoms locked in perfect geometric formation. After solidification, blades undergo solution heat treatment at 2,200 degrees Fahrenheit for 2 hours, then quench in inert gas. This locks crystal structure permanently and precipitates microscopic strengthening phases throughout the lattice. Next comes aging heat treatment, multiple cycles at precisely controlled temperatures that cause nanoscale particles to form. These particles, called gamma-prime precipitates, occupy 70% of the alloy's volume. Picture this. Imagine a 3-dimensional checkerboard where hard particles pin the crystal lattice, preventing atoms from sliding. These precipitates remain stable at temperatures where other metals liquefy. They're the secret allowing nickel alloys to maintain strength at 3,000 degrees, temperatures where aluminum vaporizes, titanium melts, and even steel becomes taffy. The heat treatment process takes 96 hours of precise temperature control. Deviate by 15 degrees at any point and mechanical properties drop 40%. Coating application transforms already sophisticated blades into thermal protection systems. First, a metallic bond coat, aluminum-rich alloy, gets applied via high-velocity plasma spray at 20,000 degrees Fahrenheit. Metal particles accelerate to twice the speed of sound, impacting the blade surface with such force they cold weld instantly. This creates a rough surface for subsequent layers while providing oxidation resistance. Then comes the thermal barrier coating, Yttria-Stabilized Zirconia ceramic, applied atom layer by atom layer using electron beam physical vapor deposition. In vacuum chambers, electron beams vaporize ceramic ingots. The vapor condenses on rotating blades, building up a coating 0.08 of an inch thick with a columnar microstructure full of microscopic pores. These pores act like thermal insulation, trapping air pockets that reduce heat transfer. The ceramic coating lowers blade temperature by 400 degrees, the difference between survival and meltdown. Modern engines couldn't exist without this coating technology. This wasn't always possible. Back in 1940, early jet engines used cast iron turbine blades lasting 20 hours before failure. Temperatures barely reached 1,400 degrees Fahrenheit. The breakthrough came when Pratt & Whitney researcher Frederick Vierling invented directional solidification in 1966, eliminating transverse grain boundaries and doubling blade life overnight. The true revolution arrived in 1982 when General Electric and Pratt & Whitney independently perfected single crystal casting. Turbine inlet temperatures jumped from 2,000 degrees to 3,000 degrees Fahrenheit, a 50% increase enabling massive efficiency gains. Modern turbofan engines achieve fuel efficiency triple that of 1960s designs. Today, advanced engines like the GE9X powering Boeing 777X aircraft operate at 3,200 degrees, with pressure ratios reaching 60-to-1. These engineering advances cut aviation fuel consumption by 65% per passenger mile over 50 years. Carbon emissions dropped by 12% when replacing older turbine blades with modern single-crystal versions in existing engines, equivalent to removing 18 million cars annually from global fleets. Airlines save over $47 billion yearly through improved fuel efficiency. Maintenance costs drop 58% because single-crystal blades last 3 times longer than conventional ones. So here's the secret promised. These blades don't actually survive above their melting point through material strength alone. They're actively cooled by air bled from the compressor, flowing through those microscopic internal channels at supersonic speeds. This cooling air, already compressed to 400 degrees Fahrenheit, seems hot by human standards but runs ice cold compared to the 3,000-degree combustion gases outside. Combined with ceramic coatings reflecting heat like mirrors, the actual metal temperature stays below 2,000 degrees, hot enough to glow orange but survivable. From molten metal to flying miracles, cycle completes. Single crystal turbine blades represent humanity's most sophisticated metal casting achievement. Objects where every atom's position matters, where crystal orientation determines survival, where manufacturing tolerances make computer chips look crude. We've engineered metal to survive in conditions nature never intended, creating materials that work at their physical limits. That's not just manufacturing, that's molecular architecture enabling the modern world's ability to shrink distance itself.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this. More than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called two airs. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steel making requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised. Every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer green skin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Janka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Every year, the world lays down over 1 billion tons of asphalt, the material that modern civilization would literally grind to a halt without. But few people know that every foot of road is the result of a complex alchemy of stone, fire, and oil. It all starts with an explosion in a quarry and ends with a hot, black mass steaming under the wheels of a roller. In this video, you'll see how asphalt is born, from blasting rock to the final roller that polishes a new road. And if you stick around to the end, you'll learn a secret that most drivers don't even know exists. Almost nothing goes to waste. That crushed old asphalt is then added to the new mix back at the plant. On average, new asphalt laid on our roads contains about 22% recycled material. The payoff here is huge, both economically and for the environment. First, it drastically cuts down on the need to quarry new stone and produce new bitumen, which saves natural resources and energy. Second, it makes the final product cheaper, saving billions of dollars from road maintenance budgets. So, every car trip you take is a journey on a complex piece of engineering that not only withstands massive loads, but is also a prime example of an industrial ecosystem where the old is constantly reborn into the new, closing the loop and making the country's infrastructure a little more sustainable. The story of asphalt doesn't start on the road. It starts in two completely different places. The first is a quarry. It's a massive wound on the face of the earth where rock is blasted out. It all begins with a loud explosion that shakes the ground for miles. Huge boulders break away from the rock face. Then, giant haul trucks with wheels taller than a person move in and haul these stone boulders to the primary crusher. This is a metal monster that crushes massive boulders into smaller chunks with its steel jaws and incredible force. But that's just the beginning. The stone then goes through a whole series of crushers and screens, giant vibrating sieves. The goal isn't just to crush the rock, but to carefully sort it by size. The result is entire mountains of clean, sorted stone, which we call aggregate. You've got everything here, from large, fist-sized rocks to fine crumbs and even dust, like sand. Each size is stored in its own separate pile. It's like in your kitchen, where you have flour, sugar, and salt, each ingredient separate, waiting for its turn. This is the skeleton of the future asphalt, making up 95% of its mass. The second place where asphalt is born is an oil refinery. When crude oil is processed into gasoline, diesel, jet fuel, and other light products, a thick, black, viscous substance is left at the very bottom of the distillation tower. This is bitumen. In its normal state, at room temperature, it's as hard as a rock. You can shatter it with a hammer. But if you heat it up, it becomes a liquid, like thick syrup. It's this property, being solid when cold and liquid when hot, that makes it the perfect glue for our stone skeleton. Bitumen is the soul of asphalt. It's black heart that holds everything together. Now, let's head over to the asphalt plant. This is where all the ingredients come together. From a distance, it looks like a complex tangled metal jungle. Tall silos, endless conveyor belts, pipes, tanks, and a central tower with smoke rising from it. It's a real factory that works like a single, well-oiled machine. Different sizes of aggregate are fed from separate bins onto a conveyor belt. But not just randomly. The whole process is controlled by a computer. An operator in a control booth inputs the exact recipe for the asphalt. Depending on where it's going to be used, a busy highway or a quiet side street, the recipe will be different. The computer knows exactly what percentage of large stone, medium, small, and dust is needed for the perfect mix. It's like baking a complex cake, where every gram counts. This mix of stones begins its journey up a long, inclined conveyor and enters the heart of the plant, the drying drum. This is a huge, long tube that slowly rotates, set at a slight angle. From one end, a powerful burner blasts a roaring pillar of fire inside, like a jet engine. The temperature inside hits 300 degrees Fahrenheit. The stone, slowly tumbling inside this drum, heats up, and most importantly, gets completely dried out. Moisture is the #1 enemy of good asphalt. Even a single drop of water can prevent the bitumen from sticking properly to the stone's surface. So, the stone has to be bone dry. After the drying drum, the hot, moisture-free stone is carried up by an elevator to the very top of the central tower. There, it passes through another set of screens for a final quality check on the sorting, and then falls into hot storage bins. Meanwhile, in special insulated tanks, our black glue, the bitumen, is being heated up. It's also brought to a high temperature to make it fluid and runny. And now comes the climax. The computer gives another command. A wayhopper, with incredible accuracy, measures out the required amount of hot stone of each size from the different bins. Then, a precisely measured amount of hot liquid bitumen is sprayed into this superheated stone mix. This entire mass, stone and bitumen, is dropped into a mixing chamber called a pug mill. It's like a giant kitchen mixer, but instead of whisks, it has 2 powerful shafts with metal paddles. These paddles churn the hot mass with enormous force, and in less than a minute, every single stone, every grain of sand, is coated in a thin, shiny film of black bitumen. Out of the chamber comes the finished asphalt, a uniform, steaming black mass with a characteristic oily smell. Now this hot, freshly made product needs to be stored until it's shipped out. It's lifted and dumped into special insulated storage silos. They're like giant thermoses that can keep the asphalt hot for many hours, sometimes even days. Dump trucks pull up under these silos. With a loud clang, a gate opens and several tons of hot asphalt pour into the truck's bed with a roar and a cloud of steam. The bed is always covered with a tarp to keep that precious heat in during transport to the paving site. At the construction site, the final act begins. The dump truck slowly unloads the hot mix into the hopper of a special machine, an asphalt paver. This machine, moving forward slowly, evenly spreads the asphalt over the road surface, forming a perfectly level layer of a specific thickness. At the back of the paver is a heavy, heated plate called a screed. It does the initial compaction and gives the surface its first pass of smoothness, but the asphalt is still soft and loose. To make it strong, it needs to be compacted. Right behind the paver follows a whole team of heavy road rollers. First come the large steel drum rollers, which use their immense pressure to squeeze the air out of the asphalt mix and force the stones to lock together tightly. Then, pneumatic tire rollers might be used, which knead the surface, making it even denser. And in the final stage, smooth steel drum rollers pass over it again to give the road its final, smooth finish. As the asphalt cools, the bitumen turns from a liquid back into a solid. It permanently glues all the stones together, turning the loose mix into a strong, waterproof monolith. After a few hours, the road that was recently hot and soft becomes hard and ready for traffic. And that's the whole point. From the explosion in the quarry to the heavy roller on the road, every stage of this process is designed to create a durable, reliable surface that will withstand thousands of cars every single day. Every year, over 100,000 kilometers of new rails are laid across the planet, and every single one of them goes through hell first. Fire over 1,500 degrees, the crushing force of rollers, and jets of water that cut metal like glass. From scrap heap to gleaming steel, a rail's journey is like an initiation, where every step decides whether it survives or shatters under the first train. But what makes this steel so perfect that it can handle thousands of tons of pressure every day without bending or cracking? Stick around, and you'll see how the arteries that move the entire world are born. First, you gotta make the steel. A mix of scrap metal, iron ore, coke, and limestone gets dumped into the furnace, the raw ingredients for a future rail. The temperature in the blast furnace hits over 2,700 degrees Fahrenheit. That's 1,500 Celsius. Under that hellish heat, the metal turns liquid, glowing like the sun. Workers keep a close eye on the composition. Even an extra 0.1% of carbon can make the rail too brittle or too soft. After melting, the molten steel is poured into molds, metal forms that create rectangular blocks called ingots or slabs. They don't look like a rail yet, just solid bars a few meters long and over a foot wide. After pouring, each blank is cooled, but not completely. It's kept warm to reduce stress during the rolling process. This stage is the foundation for everything. If the steel comes out bad, even a perfect rolling job won't save it. So quality control here is almost a ritual. Chemists check the composition, metallurgists monitor the temperature, and automatic sensors track the cooling uniformity. Only when every single parameter is locked in does the blank move on into the fiery heart of the rolling mill. In the rolling mill, massive billets, up to 20 meters long, are heated in furnaces to over 2,200 degrees Fahrenheit, 1,200 Celsius. The metal becomes pliable, like dough, but keeps its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce its thickness, then to give it the right shape. Each pass is a squeeze and stretch, gradually transforming the metal from a simple billet into a future rail with its complex profile: the head, the web, and the foot. To get the exact geometry, they use a final sizing roll. It's like the final polish of the shape, with tolerances on this step not exceeding 0.3 of a millimeter. Right after rolling, while the rails are still hot, they go through a cooling process. They're either evenly blasted with air or left to cool on an open rack. It's crucial that the cooling is symmetrical, otherwise the metal could warp. To ensure a smooth, bump-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding. In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, created by the reaction of powdered aluminum with iron oxide, is poured in. The temperature hits a scorching 4,500 degrees Fahrenheit, 2,500 Celsius. This molten metal flows into both parts of the rail and fills the joint area. When it solidifies, it creates a monolithic bond, stronger than the rail itself. After that, the excess metal is trimmed off, and the weld is ground down to a perfectly smooth level, without a single bump. Every joint is inspected, with ultrasound or eddy currents, to make sure there are no hidden micro cracks. These long rails are easier to transport than you'd think. They're either wound onto special drums or carried on platforms with pivoting supports. And on the construction site, the sections are joined again, this time by welding or using special bolted joints. The result is a continuous rail line that stretches for kilometers without a single click. The same silent glide we've come to expect on high-speed trains. But first, after rolling and welding, the rails are still alive. There's stress left inside the metal, and the grain structure needs to be stabilized. This is where heat treatment comes in, giving the rail its strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, around 1,800 degrees Fahrenheit, 1,000 Celsius. This is done in furnaces, tens of meters long, where the temperature is controlled to the degree. At this heat, the steel's crystal lattice shifts into a new state, austenite. But the main event starts after that. The rail is instantly cooled. Jets of high-pressure water are aimed along the head and web, the very parts the wheel rolls on. The temperature drops in a flash, and a new structure forms in the metal, martensite, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled one more time. This balances the structure, relieves any extra internal stress, and ensures the rail can handle frost, heat, and thousands of trains a day. In the end, the metal holds its shape and withstands pressures of tens of tons per square inch without deforming. Before a rail hits the road, it goes through a whole series of tough tests, like it's trying to join an army of high-speed transport. In special labs, it's checked for strength, hardness, geometry, and internal defects. First up, ultrasonic testing. High-frequency waves are sent into the rail. If there's a microcrack or void inside, the signal bounces back and flags the problem. Then, hardness measurements along its entire length to make sure the heat treatment was uniform. At the same time, its straightness and profile are checked. Laser sensors scan every inch, detecting even tiny warps that could cause vibration or wear. And finally, bend and impact tests. A piece of the rail is loaded with pressure dozens of times greater than the weight of a train to make sure it can handle any challenge on the route. When the rail has successfully passed all the tests, it's time for its most important journey, to the installation site. But how do you transport giant metal strips over 90 meters long? Regular trucks can't handle it. Here, they use special railway platforms with curved supports that reduce stress and prevent the rail from sagging or vibrating during transit. Sometimes, rails are transported already welded into even longer sections, from 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is to compensate for the thermal expansion and contraction of the metal. Otherwise, it would buckle in the heat or gaps would form in the cold. In practice, each rail is laid with these physical changes in mind, usually at a stress-free temperature point. Imagine this. Every year, the world cranks out over 100 million tons of nuts and bolts, the invisible heroes of our industrial world. They hold together our bridges, our planes, our ships, and even our tallest skyscrapers. But few people know that behind every single one lies a process with precision down to 1,000th of an inch. We're talking metal cleaned in acid, forged under massive presses, hardened at over 2,000 degrees, and tested to its breaking point. So what makes an ordinary bolt strong enough to hold hundreds of tons? Stick around, and you'll learn the secret that turns a simple piece of steel into a part the whole world depends on. A high-volume nut and bolt plant isn't just a factory. It's a high-tech powerhouse where raw steel becomes the hardware that holds our world together. The whole thing is a complex, multi-stage marathon of machining, stamping, heat treating, and non-stop quality control. It all starts with the raw material. High-quality steel wire rod comes in, but it's dirty. First, it needs a serious cleaning to get rid of rust and scale. The most common way to do that? A chemical bath. We're talking a process called acid pickling, where the steel gets a dip in sulfuric or hydrochloric acid. This stuff eats away all the grime, leaving the metal surface perfectly clean and ready for what's next. After the acid bath, the wire is thoroughly rinsed with fresh water to get every last drop of acid off. Then it's dried. For an even deeper clean, some plants use sandblasting or mechanical grinding. You might even see a process called electrocleaning, which zaps the surface to level it out and boost its rust resistance. On the big production lines, they combine everything: mechanical scrubbing, a chemical dip, a rinse, and a dry. And they don't just eyeball it. Quality control uses visual checks and special instruments to make sure that surface is perfectly clean. Before it moves on, the metal gets a temporary rust preventive coating to keep it pristine during storage and handling. The main ways to make a bolt are cold forming and turning. Cold forming is the real workhorse here. That's where a machine takes the metal wire and shapes it under massive pressure, all without heat. The wire feeds through a series of dies that hammer it into the shape of a bolt. First, the round shank, then the head, usually a hex head so you can get a wrench on it. The beauty of cold forming is that it's incredibly precise, makes the steel stronger, and wastes almost no material. Once the head and body are formed, it's time for the threads. Here, they use a method called thread rolling. Instead of cutting the threads, the bolt blank is forced between special dies that literally press the threads into the metal. This process makes the threads incredibly strong and durable. Some of these high-speed lines can churn out hundreds of bolts a minute. For nuts, they often use hot forging. Steel blanks are heated up to a blistering 2,200 degrees Fahrenheit. That's about 1,200 Celsius, making the metal soft and pliable. Then, a press forges the iconic hex shape. After that, a hole is punched through the middle, and the internal threads are cut on special machines called tappers. Just like bolts, nuts go through heat treatment to make them tough and wear resistant. Heat treating is where a bolt gets its backbone. It's a two-step process, quenching and tempering. First, in quenching, the bolts are heated up and then rapidly cooled. This makes the steel incredibly hard, but also brittle. So the next step is tempering. They're reheated to a lower temperature, which gets rid of the brittleness, but keeps all that strength. This is how bolts get their specific grade or property class. After heat treating, every batch goes through brutal quality control. Sample bolts are checked for size, strength, thread accuracy, and any surface defects. We're talking micrometers, go-no-go gauges, and special optical sorters. Any parts that are out of spec are either rejected or sent back for reprocessing. To fight off rust, most bolts and nuts get a protective coating. This could be zinc plating, hot dip galvanizing, or special zinc flake coatings. This is what keeps them from rusting away, especially out in the elements. The finished products are then sorted by size and strength, boxed up, and prepped for shipping. Modern plants have automated lines cranking out hundreds of thousands of these a day. The parts travel on conveyors to automatic sorting machines that use optical sensors to check every last one. Anything that's damaged or not up to snuff gets kicked out. This makes sure only top quality hardware makes it to the packaging line. From there, the nuts and bolts go into automated bagging lines with inline scales and counters that measure out the exact quantity for each package. This could be small plastic bags, cardboard boxes, or bulk bins, depending on what the customer needs. The packages are labeled with all the key info: size, grade, manufacturer, and date. For big industrial orders, they're often packed in bulk bags or large containers to make shipping and storage easier. The whole process is automated to ensure the packaging is sealed tight to keep out moisture, dust, and prevent any damage in transit. Even though most of it is automated, there's still a human touch. For special kits or custom orders, workers will manually check the quality of the packaging, assemble the right mix of nuts and bolts, box them up, and get them ready to ship out. This flexibility allows them to meet specific customer needs with pinpoint accuracy. After packaging, the products go through one last check to make sure the labels are right and the packages are sealed. Then, they're sorted in the warehouse by order and prepped for dispatch. And it's not just standard stuff. Many plants also make custom fasteners based on a customer's specific blueprints, which is crucial for specialized industries like aerospace, automotive, or heavy construction. The global market for fasteners is on a steady climb, and it's all driven by a few key things. First up, construction. As countries spend more on infrastructure, we're talking bridges, roads, and new buildings, the demand for these steel connectors goes through the roof. Second, the automotive and machinery industries. Every car, truck, and piece of factory equipment is held together by hundreds of high-quality fasteners. As those industries grow, so does the need for top-grade nuts and bolts. For example, in Europe, car production is expected to climb, which directly boosts the demand for metal products, including fasteners. At the same time, the steel industry itself is getting smarter, using digital tech and automation to produce better, more specialized products. Of course, the cost of raw materials like iron ore and energy can affect things. But at the end of the day, as long as we're building, driving, and manufacturing, the demand for nuts and bolts isn't going anywhere. Imagine this, a single piece of steel that can hold the weight of 100 fully loaded semi-trucks. How? It's all about a shape engineers call the I-beam. This isn't just metal, it's the backbone of our cities, born from rusted scrap and forged in lightning, fire, and thousands of tons of pressure. But here's the kicker. Why are brand new I-beams almost entirely made of the past? Cars from the 70s, rails from the 30s, even armor from World War II. All of it could be holding up a modern skyscraper. Stick around and you'll learn a secret that will change the way you think about the power of steel. The genius of the I-beam is its shape. The real heavy lifting is carried by the top and bottom parts, so that's where most of the metal is packed, in the flanges. The thin web in the middle just keeps them locked in place. This gives you maximum strength for minimum weight. And that strength is just insane. A single heavy I-beam, set up right, can handle loads of hundreds of thousands, sometimes even millions of pounds. Picture a whole line of fully loaded semi-trucks, all parked on one single piece of steel. That's real power. This story doesn't start in some shiny workshop. It starts in a massive, rusty, noisy yard that looks like a graveyard for metal giants. This is a scrap yard. Mountains of old cars, chopped up rail cars, building frames, and industrial junk are all waiting for a second chance. A giant crane with a powerful electromagnet drops down on the pile, and with a metallic groan, tons of old iron leap up to meet it. This scrap is the main ingredient. It gets loaded into a huge steel basket and sent to the melt shop for its trial by fire. Steel is the undisputed champion of recycling. The recycling rate for structural steel in the US is a whopping 98%. That means nearly every piece of steel from torn down buildings, old bridges, and scrapped ships gets put back to work. On average, a new I-beam made today is 90% recycled metal. This creates an incredible, endless loop. A skyscraper going up today could have a piece of a 70s muscle car, a 1930s railroad track, and even armor from a World War II battleship inside it. This isn't just a hunk of steel. It's concentrated history, melted down and reborn for a new tour of duty. So these numbers aren't just stats. They're the silent language our cities are built on, a language of strength, efficiency, and the almost endless life of metal. Every year, the United States cranks out over 5 million tons of structural steel, and the lion's share of that is I-beams. That's a number so big, it's hard to get your head around. Let's try. The steel in the famous Golden Gate Bridge weighs about 83,000 tons. That means, in 1 year, American mills produce enough beams to build over 60 Golden Gate bridges. The heart of the plant is the electric arc furnace, a giant kettle, the size of a small house, where our scrap metal is dumped with a thunderous crash. 3 massive graphite electrodes, thick as ancient trees, are lowered in from the top. And And then the operator hits the juice. An electric arc, basically a man-made lightning bolt, erupts between the electrode tips and the metal with incredible force. The shop fills with a deep, bone-rattling roar, and the light from the arc is blinding. The temperature inside instantly shoots up to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It starts to melt, turning into a boiling, blazing lake of steel. Special additives are tossed into this molten bath to get the exact grade of steel needed, strong but flexible enough to handle massive loads. When the steel is ready, it's time to turn this liquid river into something solid. The molten metal is poured into a continuous casting machine. The blazing liquid flows into a special, water-cooled copper mold. As it passes through, the outer layer of steel freezes, forming a thin skin. Next, this still mushy on the inside ingot is continuously pulled downwards through a chamber of water spray where hundreds of nozzles blast it, forcing it to solidify all the way through. What crawls out of the machine is an endless, glowing red, massive steel billet. This is called a bloom. Automated torches hiss to life and slice off pieces to the right length, say 20 or 30 feet. This is our blank, our piece of dough that we're about to shape into a beam. These hot, but now solid blooms are sent to the next furnace, the reheating furnace. It's like a giant tunnel with a fire roaring inside. The blank moves slowly through it, where its temperature is cranked back up to the perfect working heat, around 2,200 degrees Fahrenheit. It becomes soft and pliable, like clay, ready for the most important step, rolling. And this is where the real show begins. The bloom, glowing a brilliant orange, rolls out of the furnace and hits the rolling mill. This is a series of giant steel rollers, like massive rolling pins, lined up one after another. But these rollers aren't flat. They have special grooves cut into them, shaped to gradually form an I-beam. The bloom slams into the first set of rollers. They squeeze it with thousands of tons of force, making it a little thinner and longer. Out the other side, it's grabbed by the next set, which squeezes it from a different angle, starting to form the flanges and the web of the future beam. And so, step by step, passing through dozens of these roller sets, our shapeless billet is stretched and molded, taking on that familiar I shape right before your eyes. It's an incredible sight. A piece of glowing steel that started at 20 feet long gets stretched into a fiery ribbon hundreds of feet long. The whole mill is filled with a symphony of bangs, screeches, and the hiss of water keeping the rollers cool. When the beam exits the final, finishing roller, it has the perfect shape and dimensions, down to a fraction of an inch. Hot, long, like a fire serpent, it travels down a roller conveyor to a massive cooling bed. This is a giant rack where the beam slowly cools, letting its heat radiate into the air. As it cools, the metal shrinks a bit, and sometimes the beam can get a slight warp. To fix that, after it's cooled down, it's sent to a straightener. This thing is like a giant steel chiropractor, passing the beam through a set of rollers that align it until it's perfectly straight. So, we have a perfectly straight, long beam, but it's not ready to ship yet. Time for the finishing touches. First, it's cut to the specific lengths the customer ordered. This is done by giant saws with blades 6 or 7 feet across. With a deafening scream and a shower of sparks, the saw cuts through the thick steel in seconds. Then, every single beam goes through a tough quality control check. Inspectors measure its geometry, and special ultrasonic machines scan the metal to make sure there are no hidden cracks or flaws inside. Only then does the beam get its marking, its birth certificate, with the steel grade, size, and batch number. The finished inspected beams are picked up by giant cranes and stacked in the yard, or loaded directly onto special railcars or trucks. And just like that, This steel backbone, born from rusty scrap, forged through fire and pressure, is ready to ship out to a job site to become the silent but incredibly strong skeleton for a skyscraper that will scrape the clouds, or a bridge that will connect two shores. Standard beams on a construction site can be anywhere from a few inches to 3 feet tall. But then there are the real monsters, the so-called jumbo sections, used in the most critical spots of skyscrapers. Their height can be over 4 feet, and their weight is something else. The heaviest ones can weigh over 800 pounds per foot. Think about that. Every foot of that beam weighs as much as 3 grown men. And a standard length for these things is 60, 80, or even 120 feet. A single one of those beams can weigh as much as a battle tank.